everyone. Welcome to the Geospatial Forum. I'm Ross Mintermeyer, Director of the Center for Geospatial Analytics, and I'm thrilled to host today's speaker, Dr. Emily Berglund. Dr. Berglund is a faculty fellow of the Center and an associate professor of civil construction and environmental engineering here at NC State. She graduated with a BS and an MS in civil engineering at the University of Kentucky, and she's a proud graduate of NC State, where she earned her PhD here in 2005. So I first met Emily at a sustainability science workshop on the coast in Wilmington 3 years or so ago, maybe exactly 3 years ago.
That's right.
And ever since then, we've had a lot of things to talk about, including even a new National Science Foundation Smart and Connected Community grant that we're collaborating on together. And perhaps it's no surprise that I want to chat all the time. Dr. Berglund's integrated research really is an exciting nexus between social, natural, and infrastructural systems, all powered by innovative computing technologies. So the title of Dr. Berglund's forum is Networks for Neighborhoods, Simulating the Dynamics of Water Reuse Adoption and Impacts on Infrastructure Management. So please join me in welcoming Dr. Emily Berglund. Thank you.
All right, thank you for that introduction. Before I get going, can I get an idea of who you are? Are people here mathematicians, engineers, statisticians, social scientists, biologists? All of those, I guess. Okay. Well, this is, I think this talk can speak to each of you, so I'm not too worried about that. My lab in the civil engineering department is the socio-technical systems analysis lab. And so we're studying, we're building modeling frameworks to understand how do behaviors and decisions affect infrastructure, and then how does infrastructure design feedback and affect behaviors and decision making. So we're really trying to capture the full loop is what we're trying to do. And so today I'm going to be talking about this kind of a modeling framework developed for water reuse. And specifically we're looking at adoption dynamics. And so I just wanted to start from Roger's theory of diffusion of innovations, which basically simulates or models that adoption is a process that occurs in an S shape, where we start off with just a few innovators. Over time, more people come on board, adopt a new technology, and at the end you have kind of the laggards who are finally adopting. So this theory is based on the idea that the technology itself doesn't just drive adoption, but it's a characteristic of the population. And so who the people are, their characteristics, what their network is, and that influence among members really drives the adoption. And so there's an external factor, which is maybe ads, campaigns, and internal factors are those social dynamics. So this model has been applied to simulate or understand a number of technologies as they've become widespread throughout the population: radio, TV, VCR, shown here. But also is applied to understand, again, or simulate how the adoption of more infrastructure-related technologies has occurred, such as the railway network follows an S-shaped curve in its distribution across the U.S. The electrification of U.S. households, again, follows that S-shape, and even things such as the indoor plumbing follow this shape. As an engineer, I'm very interested in what technologies are affecting our infrastructure systems. And so a lot of times this is eco-innovations, environmentally friendly innovations or technologies. And so infrastructure networks are built to deliver a resource, transportation, water, electricity, getting rid of waste, getting rid of solid waste. So all of these infrastructure systems are connected to natural resource consumption. And so as we start changing the way that we're consuming some natural resource, then that affects the infrastructure system. so once we start seeing widespread adoption, that can cycle back and affect the infrastructure itself. For example, there's a study of a city in Europe where water reuse technologies were used, and the discharge to the wastewater sewer system decreased so much that the velocities decreased in the sewer system, and the solids and sediment were settling in the system, created the infrastructure to fail. So we see there's this feedback in certain instances. The next kind of prong, where we need to expand the kind of typical diffusion modeling is in the spatial direction, and that's where infrastructure systems, if we want to model eco-innovations, infrastructure systems, then now there's a spatial dynamic that the original model doesn't take into account. One concept is that a lot of eco-innovations might be spread more through a neighborhood than a network. So if you think of sprinkler systems, solar PV systems, electric cars, these are things you might see your neighbors have, not just something you would read about your friends having on a social media or talking about over dinner. So there's the spatial dimension to your neighborhood. And then maybe more importantly is that the location of the demands and where conservation is occurring affect your infrastructure. If you think of households adopting solar PV, if we have a cluster of households that are adopting, then they're changing how they're using electricity from basically one distribution wire. And so if all those households are putting energy back into the grid, that can be a lot of energy and fry those wires and create a lot of problems for the grid. So there's a spatial dimension that has to be incorporated in the model. And so that's the model that I'm talking about today. We have the social dimension of adoption, we have the technology, or the infrastructure network, and the spatial dimension is needed. So today I'm going to talk about water reuse. And so what we're talking about, just to make sure we're all on the same page, is wastewater that's treated to some standard so that people can use it again. So there's different ways for wastewater to be treated for drinking water. More commonly in the U.S., we treat it to a lower standard and use it for non-potable purposes, irrigation and cooling. The adoption of water use has a very interesting social dynamic. And so I'll just pause and ask, would you drink water out of a toilet even if that toilet were brand new, never been used?
Depends how thirsty I am.
All right, and so the answer to that question is not necessarily yes for everyone. You might be surprised. But water reuse is a great way to balance demand and supply, to provide a sustainable way forward for using our water resources. But there's what has been termed a yuck factor, and that is just the idea of just distaste, or the idea that something's dirty, even though you might cognitively know it's fine, like it's good to go. So that yuck factor adds kind of a dimension of overcoming that in order to adopt water reuse. But research shows that perceptions can change over time based on familiarity with water reuse or campaigns or seeing other people use this. And so from an infrastructure perspective, to integrate water reuse into an existing water supply system. So you have your drinking water network, and now we want to integrate another source of water, another type of water. It's usually, or often planned out in phases, where we would want to see that distributed through the network over time. A lot of this is intensive infrastructure, and so it's something that takes place in phases. So in this, the research that I want to talk about, we're asking a couple questions. First, how are consumers using and adopting water reuse? And then how should we plan expansion of our systems based on that we can understand or project how they're adopting water reuse? Some other research we've done looked at the effects on the infrastructure, so the pipe networks. What are the new what's the change in the flows, the change in the pressures. But today I just thought I would focus on the expansion plans. And I'm going to be talking about two complex adaptive systems models. And so this is what we're using to simulate behaviors in the system. The CA model, or the CA system, represents your landscape as a grid, and each cell is effectively on or off and is updated through a transition rule that looks at the neighbors of that cell to update its state. Agent-based modeling is similar to CA, but has what you can think of as more flexibility. Agents could be mobile. They can take on many different characteristics, have rules that define different behaviors, and we can see a lot more variability and heterogeneity. Still, we can explicitly locate them spatially. So I'm going to use a CA model to look at a neighborhood distribution or diffusion of water reuse, and then an agent-based model to explore how social networks can affect adoption. For a CA model, we just represent each household as a cell that transitions from a potential adopter to adopter. Neighbors pass messages if they do adopt, and so each time step represents a month, which would correspond to a water bill. And it's a fairly simple model where we have that internal factor, which is how many of my neighbors have adopted, and that external factor is represented as a random variable here. So if the sum of a utility function is greater than a threshold, then that cell becomes an adopter. So how this works is that we have a grid that represents the entire city, but only a small portion of that grid has access to reclaimed water. The infrastructure has only been built out to that phase. And so we start with potential adopters and adopters. Over time, the cells become adopters. Maybe all of them have adopted here. And then we go to the next phase of expansion. So now all of these, the rest of the network is initialized as potential adopters or adopters. And again, we start the communication phase over. So there's here with the neighborhood effect, what we see is that the previous community that had access to the infrastructure doesn't really affect the new community that much, except for their bordering, right? The agent-based model that I'm going to talk about is based on the theory of risk publics. This is a theory that Dr. Bender here in the Department of Communication has been working on for a while. And so this theory splits the population into clusters, and people in those clusters have similar perceptions of the risks and benefits of a new technology. And so this theory goes beyond the diffusion of innovation theory, because we're giving more heterogeneity to the population. They can have different initial starting points for their perceptions of both risks and benefits. So it's taking into account more characteristics of the technology. And we have communication within clusters and among clusters. And so people in the theory, the idea is that people can update their opinions. You might start off as thinking it's a really bad idea. Over time, your opinion changes, and so you think, oh, this is a good technology, we should all get on board. In order to parameterize this model, so the CA model is fairly simple. The agent-based model is more complex. So we have basically a lot more parameters in that model to define how agents are changing their opinions. And so we conducted a national survey about the acceptance of water reuse to come up with these clusters of perceptions and to use that for parameters in our agent-based model. So this is based on the survey, which was almost 3,000 people across the U.S. We have 4 clusters. The optimistic cluster perceives low risk and high benefit of the technology. The alarm cluster, on the other hand, just sees high risks and low benefit, and this survey was specifically about water reuse. So this is their perception of water reuse. There's a cluster of conflicted individuals who see high risk or moderate risk and moderate benefit to water reuse. And then a disengaged cluster who is kind of neutral on all sides, not really that concerned about this technology. And the breakdowns of these clusters are similar to other technologies that Dr. Bender's conducted surveys about. So we wanted to convert this theory of risk publics to an agent-based model where we can look at how opinions are changing over time as agents talk about water reuse. So we have the 4 clusters: optimistic, conflicted, disengaged, and alarmed. And so we assign each agent to one of those clusters. And then each agent is also assigned to a small world network. So the cluster defines their perception of risk and benefit based on that survey. The small world network defines who that agent is connected to share information about the technology. Agents send messages with frequency based on their cluster. So in the survey, we asked how often people are talking about this technology or related ideas. And so from there, we got a relative frequency of talking about water reuse that we could use in the model. And so then we update perceptions of risks and benefits for each agent using these equations here, which capture your starting perception of benefit and risk, and then the messages that you've received about benefit and risk from other agents. And this div factor on the bottom there is a discount factor that basically weights more highly opinions from people like yourself. So if the message is received from a cluster outside of that agent's cluster, then that agent would discount that opinion and more highly count opinions from within its own cluster. So within a cluster, different agents have different values of benefit and risk, but they're only different by a small margin. So here, kind of looking through how the model works. Similarly, we can think of an initial neighborhood that has access to the infrastructure, but now we have more heterogeneity among each of our cells, right? Each agent or cell would be one of the clusters and is connected to other agents throughout the neighborhood. So instead of just having information from your north, south, east, and west neighbors, you would have, or each cell would have a connection to a number of cells in that neighborhood. So again, we have expansion of the infrastructure. These cells can communicate, and we see some become resistors. And here in this model, we've added the idea of a resistor and an adopter. So not just the idea that a potential adopter and adopter, but the risk publics theory includes the idea that some people are going to be resistors, not going to adopt. And some people are going to finally become adopters. And so we allow the model to kind of tip either way. Right? The CA model just says you can tip all the way to full adoption. But here we allow, if we have the right conditions, the resistors could kind of take over and shift public opinion. And that's what we show in some theoretical paper. For this system, we're not going to see that happen. But the network expands. We add more agents to the communication pool and watch the adoption emerge. Now the difference between this and the CA model is that when we reinitialize the network whenever we have an infrastructure expansion phase. So infrastructure expansion happens in maybe 5-10 year phases. And so the idea is that over 5 years, your social network may change in nature. And so we reinitialize the network every phase. And that allows adoption dynamics to migrate from areas that already had the infrastructure to now areas that are new to having the infrastructure. So the system where we're applying this is the Cary reclaimed water system. Anybody here live in Cary? Oh, I'll just one, okay. Do you have reclaimed water at your house? Not that you know of. So this is not available to everyone in Cary, but this is a dual system, which means we have your drinking water pipes bringing potable water to your house. For this system, there are a second set of pipes that are bringing reclaimed water to your house that you can use only for irrigation, not for potable uses. So for households where this network exists, they can start an account and tap into it. And so we're calling adoption, we're referring to that here, but that refers to when they began their account, started to use reclaimed water. So this is planned out in phases. Here are the, so I'm using a master plan that has, since we started this research, been replaced. So when they started this plan, this was how things looked in 2007. This is the Cary reclaimed water treatment and is piping water to these homes. This water is coming from a treatment plant in Durham, so it's not part of the Cary system at this phase. And so the idea is that in increments they would expand the system and go from a small cluster. In 2015 they would build the pipeline that connects the east and the west, and then continue to build up demands in the network. And so by 2025 we would have a much larger population with access to the reclaimed water system. By 2030. So we wanted to apply our model to this case study. So we collected some of the historic data. So here we have the property information about where the lots are, and we glean from this how many neighbors each cell has, and that for this system is just irregular. Neighborhoods take on different shapes and forms, and so not every household has the same number of neighbors. We overlaid that with network data, which tells us access that different houses have to the water reclamation infrastructure. And so in 2001, you see some neighborhoods came online, had access, and in 2005, these secondary neighborhoods had the infrastructure available. And here's the history of accounts that were started on just an annual basis, going from 2001 up to 2012. So we applied the CA model to simulate this data, and I'm just showing two of the models here. We calibrated the model, so we had a number of models with different parameter settings. But here on the top is the CA model 1. This one has the lowest error of all the models. And this one was governed by that internal factor. The internal mechanism was really driving the adoption for the CA model 1. And you can see here the weight on internal factors, the messages, is higher than the second model. And the other parameters that we looked for were probability of accepting messages. So we do have the concept that you might receive a message and ignore it. And then the threshold for the number of messages that are received before adopting. The CA model 2, on the other hand, the external factor is really driving adoption here. And so what we're doing here is, we want to parameterize what's basically a social model. And it's pretty hard to go back and say that you've parameterized it correctly except for the error value, right? That's how we calibrate models, is look at how well it did compared to your historic data. But for social models, there's not a way to go back and make sure that everybody really did adopt water use because of internal factors and not external factors. Like that, that's not something that translates well. And so what we're doing here is exploring what are the different pathways to get to the same outcome. And so that's what we looked at the CA model, where the different factors that could affect adoption, and then looked at the risk publics model. And so here again we had a bit more complicated model. The number of messages per year, that discount factor that I said, which more highly weights messages from your own cluster, and then population proportions are all the numbers that we looked at to calibrate the agent-based model. So first what we did is look at the population proportions in clusters from the survey data. And I just whited out some of the other parts of this table so it wouldn't be too confusing, and just focused on the South Atlantic and mountain regions. So South Atlantic is where Cary is located. So hypothetically, Cary would have that population breakdown of optimistic, disengaged, alarmed, and conflicted. This didn't work very well, so we also looked at the mountain region, which had the highest percentage of optimistic in the initial populations. And so we're just looking at what's going to work best to match the data. And so here's the South Atlantic. If we apply the South Atlantic population proportions, that's what you see here. And then we parameterize the number of messages per year, how much the agents are talking, and that discount factor. So for the South Atlantic, we don't get that great of a fit. And there's a good amount of talking, and then there's a high discount. So they're really weighting within the cluster opinions more highly. And similarly for the mountain region, the performance is not much better. It doesn't look any better. And we parameterize those messages and the discount factor. But we're starting to get an idea about how the model is working. And finally, we just decided to calibrate those, the proportion within the clusters and not use the survey data. And that fit the model much better. And so kind of surprisingly, what you see is there's a higher population of disengaged members. They're communicating quite frequently, 24 messages per year, and they're pretty much equally weighting messages from outside the cluster with messages from within their cluster. So again, these are three different pathways to similar models. What actually happened, again, we won't know. But this helps us to understand, okay, how can we start to project forward? And that's really where we want to go with this. So the models that I showed ended at 2012. So we're starting here at 2010. That was 500 households. Cary had, when we were going through this research, Cary had planned to increase capacity up to almost 18,000 households. So that first set of data was quite small compared to what they're planning to do. So the gray line shows the increase in capacity. So there's kind of this step up in infrastructure availability every 5 years. And then we just apply the models that we developed, the CA model 1 and 2, and the agent-based model to project adoption given that there's new capacity available. And so we see fairly different dynamics for these three models. The difference between the two CA models, you can see, is pretty significant. The internal factors that are involved in Network Model 1 are driving adoption much more quickly than the external factors of Model 2. And the idea here is that both those models did pretty well for the data, but are based on different driving forces. And so when we move to project, we get something that looks pretty different. One projects 100% adoption, the other model doesn't. When we look at the network model, remember that the network model takes the adoption that occurred in previous phases and lets those agents interact with the agents that now have access. So you can get faster diffusion with the agent-based or network model, and that's what we see is that when new phases come online, the adoption curve is much steeper. The adoption can propagate a lot more quickly through those mechanisms. All right, so again, these are different ways to model the process. We couldn't really say one's better than the other. One was more accurate. The neighborhood model is more accurate based on the data we have. But for projecting forward, it's really missing a lot of potentially important dynamics. And so, I don't think the idea of the research is to say one's better than the other, but more to say these are different ways to explore adoption dynamics. Let's look at it further in future research. From the engineering side, what's the importance of these adoption dynamics, right? And so really what we want to look at is how should we be planning our infrastructure expansion if we are able to say something about the adoption projections. And so infrastructure management in this case would have two goals. One, we would want to maximize the amount of water that's reused, right? So anything we reuse means we're minimizing our withdrawal of freshwater resources. So, we want to maximize the total amount of water that's reused, and we want to minimize the amount of infrastructure that we have out there that's not being used. So we want to minimize the capacity that's not utilized. And so we just represented this pretty simply as the reclaimed water utilization is just the sum over all the years of the total number of adopter households. So the sooner you have more households adopting, the higher your metric would be. For unused capacity, this is just going to be the amount of capacity that's available, the number of households that could be served, minus the number of households that are served at each year. And so a greater deficit summed over each year would be a worse performance. And we looked at 11 scenarios compared to Cary's master plan. This is a little confusing, but it's been difficult to figure out how to present this information. I will point out the orange triangle line is Cary's master plan. So that shows at 2010, they were almost at 50% of the full build out, which was about 18,000 homes. And then in the next phase, they bumped up just a small percentage, maybe 8%, then a large jump up, and finally in the last phase, they increased by another about 15%. So that's Cary's master plan. You can compare that to the turquoise square line, which is the uniform. And so that just shows every phase there's 25% increase in the amount of capacity available. We're going to also look at the full initial, which is just the top line saying, hey, if our goal is to maximize use of reclaimed water, just make it all available all at once. So not taking into account that's a massive amount of construction that would have to be done all at once. Would that be a good plan? The other scenarios that performed well are the Q1, Q2, and Q3. And here, these scenarios are all starting at 25, 50, or 75, and then just going straight to full build out after that first quarter. So these are the plans for expansion. And so just looking here at the, this is the full initial scenario. So that means right at 2010, let's assume we can put all the infrastructure in the ground, provide reclaimed water to all 18,000 homes. What are our adoption dynamics going to be? How are they going to play out? And so what we see is relatively quick adoption, but we have a lot of infrastructure capacity available that's not being used for those first couple of years. But that quick diffusion comes from all the homes are active in communication from the very beginning. So just you can get that momentum going, and then everybody comes on board around 2015. So here we looked initially at the full initial. Here's the uniform, which is just that 25% increase every phase. And here's Cary's master plan. What you can start to identify is that we have quick adoption, but in some cases that adoption is kind of tampered by the amount of infrastructure available. So you can see it kind of levels off instead of keeps increasing. So with the Q1, Q2, and Q3, there's different dynamics with the amount of infrastructure there and how the adoption dynamics can play out. All right, and so we just looked at these scenarios based on our two objectives. So the best, the ideal solution would be somewhere up here. That is, we want to maximize the amount of reclaimed water that's being used. We want to minimize the amount of capacity that's not being used. And so we can see here the full initial has the highest value for reclaimed water usage, but has quite a lot of capacity that's not being used. So Q3, which was this plan here, so build up to 75% in the first phase and then go to 100%. So that one you can see has only a slight decrease in the amount of reclaimed water that's used, but has a nice decrease in the unused capacity. So what's going on there is that this limit here of the 75% is only limiting the amount of adoption by a small amount. Over here on this side, the uniform has the lowest amount of unused capacity. So that stair step makes it so pretty much every time you have your next phase, everybody comes on about as fast as they can. And we can look at the Cary master plan, which is similar to that, the uniform, if you remember the shape of the curve. But it's dominated by Q1. And so given what we can model or understand about projections, Cary could do potentially better at planning out their expansion based on this analysis. And so that's what we kind of what we want to take home from this study is a decision tool that we can use to assess infrastructure planning based on these complex dynamics. All right, and so that's where I wanted to end and give you the chance to ask questions or talk about this. As I mentioned, we were able to compare here the network versus neighborhood effects on the diffusion dynamics. Again, we didn't make a strong case for either one, but said there's different pathways to get to adoption. And so I think it's important to understand those different pathways. And also, if you don't have a national survey to go off of, maybe a CA model is a good place to land. This provides a new decision support tool for planning out expansion and has application to other areas of infrastructure. And specifically, I think this speaks to other eco-innovations and how they relate to infrastructure. There are a couple other students in my lab. One's working on water conservation behaviors and how those diffuse through a population. And of course, that impacts your drinking water infrastructure, right? How much water is left in Falls Lake? When are we going to have the next shortage? Can depend on how all of us are watering our lawns or not. Another student is looking at the solar PV systems And again, the idea that adoption of solar PV for residences, it can diffuse through neighborhood. There might be the social network effects, but the clustering of solar PV can be really damaging to the grid. And what we see is those damages feed back into the costs of how much we're paying for electricity. And then another area we've been working on is looking at the adoption of green infrastructure. And again, this framework applies in the sense of lot level technologies such as permeable pavements or rainwater harvesting or rain gardening. Those are wonderful technologies. Where they're located in the watershed matters, but more importantly, if you have 1 or 2 people implementing that in your neighborhood, you're really not going to affect flooding very much. And what you need to see is a critical mass of adoption and evaluate those effects that way. So with that, I'll go ahead and stop and see if you have any questions.
So I'm not super familiar with the cellular CA type of modeling, but I'm just curious if there are ways to incorporate other factors such as policy interventions into your modeling. So for example, what if Cary decides to implement a policy where if you're hooked up or you're close enough to be able to hook up to reuse, you have to use it for various purposes.
Sure.
You can't choose between one or the other.
Right.
Are those kind of things, can they be incorporated into this?
Well, I mean, I think if it were something like that, there wouldn't be really a problem to study.
Yeah.
And if it's mandated, you have to do that, and it's the infrastructure is all determining that the actions, then you probably won't. It'll just be stair steps instead of an adoption dynamic. But I mean, other factors I think should be incorporated. Something that we didn't capture in any of our models is the spike in 2007, and if you know what happened in 2007 was a drought. And so, including that in the model could be important. And the students working on water conservation for a similar framework is including a binary, there's a drought or not a drought kind of thing. But that was something in this framework that we never kind of got our hands around.
Is there a way to use this to predict which neighborhoods are most likely to adopt?
I would say yes, but I think you would. So one thing that I feel that we couldn't again get to that I think would have been nice is looking at like income distributions and how those affect adoption. Cary is pretty homogeneous, so the neighborhoods that we were looking at were very similar, so there wasn't, that was a limitation, the homogeneity of Cary. The national survey has that information, but going from that down to one city, it doesn't map well. The other thing really was that Cary was very nice to work with us, but they wouldn't give us all the data we wanted, so we can have like each person's information, that kind of, utilities will share that, but it's kind of, sometimes they will and sometimes they won't. And so that kind of data would have, I think, made the model more informative to answer those kinds of questions.
So thinking about all this, so use the cellular automata and agent-based modeling. In the cellular automata, algorithm seems to be a whole lot simpler than the agent-based model, and that's the way that you guys set it up, I understand. But it all comes back to the accuracy at the end. And I was just wondering, you didn't talk about the accuracy of any of this. So based on your analysis, your Q2 or Q3 seems to be better than the plan that Cary has in place. Right. So I'm just curious about the accuracy and see if there's any way to, since some time passed since they they started this plan,
yeah,
if there's any way to kind of backlog and see the accuracy of these models that you created and calculate, or at least to give us an idea how accurate these models that you created were.
Right. So the only data we had was what I showed, which was just for the 500 households, and so that was from 2001 to 2012. And so that, I would say that's a bit limited because it's just 500 households. And we could see that the CA model has a lower error value than the agent-based models. We just essentially couldn't force the agent-based models any lower on their error values. They were about twice as inaccurate as the CA model. And those were run for, I did present kind of simply that information, but those were 10 random seeds. We did tests of a couple thousand different combinations. It was pretty extensive to try to get a better and better error. That was about as far as we could push it. So this project ended. Before it ended, Cary came out with a new master plan that's quite different from this one. And so, yeah, that would be nice to be able to go back and say, here's what we projected would happen. But that's not to say we couldn't just go back and apply the model for their new infrastructure expansion. That should work just fine. So, yeah, I think that would be fantastic to go back and look at that. But we can't compare what we have now to what they've done.
So I was interested, did you see any spatial patterns in your survey results? So you showed us that there's different regions,
right,
different percentages in your 4 groups. Are there interesting patterns there that need to be understood on environmental conditions, water stress in local towns, regions, states?
Yeah. So we wrote a separate paper on the survey and did analysis like what you're talking about. So that doesn't play into the dynamic model here. I mean, just giving that caveat. But yeah, we did find, I think, really interesting results. And this was, I think, notable because it was a nationwide survey. It was representative. And so we could compare the Palmer Drought Index, if you know that, a drought index, with adoption behaviors, or I shouldn't say adoption behaviors, but willingness to adopt, basically. And so we could look at that across the nation and see there was actually a strong correlation between the drought index, a dry year, and acceptance of reclaimed water. But there are, it's kind of a lot of results coming out of that survey of correlations of what adoption of or willingness to adopt reclaimed water is related to. But that drought index was something that others hadn't really compared, and we could do that with such a large sample. But what we showed, the South Atlantic and that kind of thing, those are the EPA 9 regions, and we couldn't get smaller than that because then our results were not statistically significant. Like Rhode Island had 2 survey participants, so it was broken down by state, and so it kind of loses meaning after a certain amount of breaking down. So regions was the best we could do. Was there a hand over there?
Oh, could you, following up on Nick's question,
okay.
Was the resolution of the actual data that you have about adoption, was that geolocated well enough that you could actually see the spread through time? And if so, did it move like you'd expect, like neighbors, affecting neighbors? Did it spread in that way, or was it more random coming on and off?
So it wasn't as fine as we would like to be able to show those results, or I would have for sure. It was more based on the neighborhoods, and so we could see the number of people through those neighborhoods.
I got you. And the messages that M sub risk, M sub benefit, is that just a negative 1 and 1? Like you got a positive message, you got a negative message, or is this?
I think it was a 1 means they adopted and 0. They didn't communicate if they didn't adopt for the CA model.
I see.
For the risk benefits model, they're communicating just their opinion. Risk, they have an opinion of risk, like a value, and an opinion of benefit, a value.
Okay.
So the CA model just sends a message, a 1, when they adopt, but the risk benefits is more about opinions diffusing through a network, not just adoption or not adoption. Yeah.
Could you imagine an interactive tool that would allow you to explore interventions in the network at particular places at particular times? Would something like that be useful to the researchers and the stakeholders?
I mean, from a utility perspective, I think if you could do something interactive with different plans, like if you plan thinking more, instead of just capacity like this, but where the showing where the network is and how it's growing, especially if you could start to incorporate some of the differences between neighborhoods. From the utility perspective, I think that would be a really valuable tool. And then other interventions I think would have to be incorporated in the model. So, something that should be there is campaigns about water reuse, And so if we did this kind of campaign, targeted that neighborhood, how would that diffuse through the network? That kind of would be, I think, valuable, yeah.
Right, and then be able to visualize,
Right.
quantify that.
Yeah, see it spread through.
Yeah.
Yeah, definitely. Yes.
So I'm just curious about the implementation of all this.
Okay.
For the CA algorithm and the ABM, did you use a platform or did you guys write your own code or some of each?
Right.
And what
So-
about it?
Sure. So we used an existing agent-based modeling platform called AnyLogic, and so then we were using that in my group, and it's proprietary, so has a cost for a university license. We've started using Mason since then, but AnyLogic was providing a lot of what we needed, which was like drag and drop kind of modeling. But it has a Java base, and so you can encode your own methods in it, which was really helpful because then you can specialize it, customize it to what you're doing. So we encoded it in AnyLogic. Here with the expansion plans, we could just import that as data. We also coupled it with pipe network models. So EPANet models flows through pipe networks. And so we coupled it with that to calculate impacts on like how much water is left in your tank, what's the pressure at different points in your network. So that was I didn't talk about that today.
And for the CA?
The CA we also did in AnyLogic. It provides that. It can do CA, ABM, and discrete event modeling.
Thank you.
Yeah. Oh.
So the graph showed that the adoption rate increased soon after the drought got bad?
Yeah.
Okay. And so is there a concept or a way to put in, even maybe with a custom Java function, the idea of perceived benefit versus benefit? And would you say that's what happened? It's like people started saying, oh my gosh, I can't water my lawn.
Right. I mean, I think there is a perceived benefit and a benefit, but as far as I think from an individual level goes, it was more, I would say that was more of their perceptions changing. Their perception of the benefit suddenly became much higher, yeah. And maybe the risk didn't matter as much anymore. But yeah, I think that if you could show the effects of drought on the dynamics of opinions, in addition to the effects of social influences on the dynamics of opinions, that would be really powerful, yeah. Yes?
So looking at this model, would you think that, expanding the reclaimed water network is one way of having people sustain their yards, right?
Yeah.
But
Oh, yeah.
alternative to that is to have the green water structures or changing the landscape that people do. So instead of doing grass, people can do bushes that are drought resistant and things like that. So
Right.
there are a lot of different ways of approaching the problem, and having the reclaimed water is only one of them. So it looks like the modeling that you guys did only just looks at that. Is there any efforts to look at a bigger picture, to look at the water problem overall?
Sure.
And treating the expansion of reclaimed water system as one of the components?
Right. I mean, not that I know of in this kind of framework, but more from an integrated water resources planning approach that looks at, reclaimed water more holistically. Like I could serve 20% of my population their outdoor water needs using reclaimed water versus encouraging drought resistant species or more restrictions on lawn watering. I think there's some of that, but kind of from a much higher level than something like this. Yeah. And yeah, I mean, these numbers are hard to get your head around too. Like how much, so this is very expensive. This is a very expensive way to provide alternative water. How expensive are drought resistant plants? like not that expensive to buy. How much is it going to cost you as a city to get that to work? Like propagate through your community. That I don't. Like, what's the cost of that? I don't know. So I think probably cheaper than infrastructure. But evaluating these things through a framework, I don't see that a lot. Yeah. Yeah.
Do you think this research would have looked different in California, a place where people are maybe a little more sensitive?
Yes, I mean they definitely have high, they're much more familiar with water reuse than people in the East are, for sure. But just looking at things for example, in Orange County, they have a water reuse program where they pump the treated water into the groundwater system, and it trickles through, and a couple years later they pull it back out, basically. So an environmental buffer like that makes people much more comfortable with using reused water. So even though they're more comfortable, they had to do a whole lot of PR to get that system going in there in San Diego, which has a surface water where they dump it in a reservoir and then pull it out of the reservoir later. So again, there's a bit of an environmental buffer. So even in California, I think they've had to do a whole lot of PR to make those things work. There's still this the yuck factor that affects the people's willingness to want to be a part of it. But in Singapore, for example, it's like part of their national identity is water security issues with where they get their water, and so like more direct reuse, like toilet to tap, even though that's not a great name, is much more accepted there. And yeah, so they have a lot more going on in different places, different parts of the world.
Time for one more question.
Okay.
Yeah, Georgina.
I was wondering how receptive was the Town of Cary to your results? I don't know if you have shared results recommendations.
So we've met with them and talked about this research and have worked with them more to understand how much reclaimed water people are using. So we've carried this on in different dimensions. I think the feedback isn't that great because they changed their master plan in the middle of our research. So I think that kind of really hampered what we could say to them. I mean, we have a nice modeling framework, but that's kind of an academic thing to say, is I have a nice modeling framework. So until I think we go back and evaluate what happened or their new plans, then I don't think we have a lot to say to them. I mean, we've shared these manuscripts and everything with them. Like, they know what our results are, and they've been very like not edited, but kind of made remarks like, oh, you kind of described this wrong, what's going on in the city. So they did actually read what we had written, but as far as that advising what they do next, that linkage isn't there.
Join me in thanking